Switzerland Swiss Mathematical Olympiad Final Round 2021, problem number 5. The problem is the following: for which integers n greater than equal to can we arrange the numbers 1, 2 to n in a row such that for all integers k between 1 and n, the sum of the first k numbers in the row is divisible by k. So we want to solve these problems like the IMO problems, IMO 2021 and also other years. I said the most important idea is to check the problem for small examples, sometimes special cases. Here we have n, so let's check that n for small example of n. If n is 1, that's possible, but the problem says n is greater than equal to. So let's check n2. We have 1, 2 or 2, 1. And if you pay attention, if k equals 2, 1 plus 2 is 3 and is not multiple of 2, because the problem says the sum of first k numbers in the row is divisible by k. But if k equals 2, 1 plus 2 is 3 and is not divisible by 2. So 2 is bad. And 3. When n equals 3, we check 1. If we place 3 here into 1 is divisible by 1, like the things here. 1 plus 3 is 4, divisible by 2. 1 plus 3 plus 2 is 6, divisible by 3. So 3 is good. If we check n4, we have 4 elements. 1 plus 2 plus 3 plus 4 equals 10. And if k equals 4, these 4 numbers, the sum of them must be divisible by 4, and 10 is not multiple of 4. So it's contradiction. Now we guess that if we consider 1 plus 2n, it is not divisible by n when n is even. So let's check that. So when you consider small examples, you pay attention that when the problem is true, when the problem is not true, and find many things like here. So let's check. If n is even, so n equals 2q. n must divide when k equals n in the problem. N must divide 1 plus 2n. So n must divide n times n plus 1 all over 2. So if you replace n with 2q, 2q must divide q times 2q over 2 would be q. q times 2q plus 1. Let me select this one. Okay, so 2q must divide 2q over 2 would be q times n plus 1, 2q plus 1. And if we divide both sides by q, then we would conclude that 2 must divide 2q plus 1, which is a contradiction. So we've proved that for n when equals n, the problem is not true. So we need to consider only when n is odd. So we know that for n1 that was true, for n3 that was true, and now we want to check when n equals 5. We say, okay, we know that 1 plus 2, 5 equals 15, and it is divisible by 5. That's true. Now, if k equals 4, the sum of these 4 numbers must be divisible by 4. So it is 1 plus 5 minus 8, if the last element is 8. 1 plus 2 plus 5 equals 15 minus a. 4 divides 15 minus a. We have 4 elements, 1 to 5, so a is between 1 to 5. And since 4 divides 15 minus a, so 15 minus a is a multiple of 4. The only a that satisfies this divisibility is a equals 3. Now let's check b. We know that 3 divides the sum of these 3 elements, and also we can say these 3 elements equals 1 to 5 minus a minus b. 1 to 5 is 15. A is 3. So 15 minus 3 minus b equals 12 minus b. 3 divides that. So b can be 3 or 6, but we know that b is between 1 and 5, so b equals 3. And a and b are equal now. This is a contradiction. Now we guess if we proved that for when n is even, the problem is not true. Now for when n is odd, we proved that the last, if n is greater than equal 5, these two numbers are equal and we can reach contradiction. So we guess that the only n that satisfies the problem is n1 and 3, but the problem says n is greater than equal to. So the only answer is when n equals 3. So let's check that. We want to look, we found the idea by these small examples, and the problem can be solved only by considering these two elements. Now we generalize these things in our exam paper. It is for ourselves. We don't write these things in our exam paper. We only consider them for ourselves, and then when we found the idea, then we write that for general n in our exam paper. So let's check for when n is odd and n equals 2k plus 1, and we can say k is greater than equal to, because we've considered for k equals 1, and we know for k equals 1 n is 3, and the problem is true. We want to prove that for k, when k is greater than equal to, that problem is not true. So let's check again this one a, this one b. N is 2k plus 1, and okay, so let's check. N divides 1 plus 2 plus 2n equals n times n plus 1 over 2, all over 2. If we replace n with k is an arbitrary integer, arbitrary positive integer here. So we replace n with 2k plus 1, 2k plus 1 divides 2k plus 1 times 2k plus 2 all over 2. 2k plus 2 over 2 is k plus 1. And let's check 2k plus 1 divides this. So for 1 to n, that's true. Now let's check for the first n minus 1 elements. We know that n minus 1 must divide, from the assumption of the problem, 1 plus 2 plus 2 condition of the problem, to n minus a, the sum of these n minus 1 elements. So n minus 1 equals 2k. Since n equals 2k plus 1, 2k divides 2k plus 1, 1 to n, times k plus 1 minus a. And we know that 2k divides 2k times k plus 1. So we can cancel these 2k times k plus 1, and we reach 2k divides k plus 1 minus a. So let's check, and we know that a is between 1 and n, means 1 and 2k plus 1. So we know that 2k divides k plus 1 minus a. We can say k plus 1 minus a can be minus 2k, minus 4k, and 0 from here, 2k, 4k. If we check these three spatial numbers from this one, k plus 1 minus a equals minus 2k, so a equals 3k plus 1. But 3k plus 1 is greater than 2k plus 1, and it's contradiction. If you consider minus 4k, minus 6k, a would be greater, and again contradiction like this. If k plus 1 minus a equals 0, then a equals k plus 1. K plus 1 minus a equals 2k, then we can conclude that a equals minus k plus 1, and we said k is greater than equal to, so a would be negative. And if you consider 4k, a would be more negative, smaller numbers, so again we reach contradiction. So from here we've concluded that a equals k plus 1. Now, like the case that we check for small example n5, we need to check this number. If we call this one b, then we need to consider the condition of the problem for when n equals for n minus 2 first elements. Now let's check. N minus 2 divides 1 to n minus a minus b, exactly our proof, like the proof for when n equals 5, a small example. Now we want to prove that a equals b. So if you replace n with 2k plus 1, 2k minus 1 divides 2k plus 1, 1 to n. It's 2k plus 1 times k plus 1, n times n plus 1 over 2. Minus a, we proved that a equals k plus 1 minus b. And if you factor from k plus 1, it would be 2k times k plus 1 minus b. And we know that 2k minus 1 divides 2k minus 1 times k plus 1. If you subtract these two terms, we would conclude that 2k minus 1 divides this, the first thing minus this thing, would be k plus 1 minus b. Now k plus 1 minus b can be minus this, minus 2k minus 1, minus 2 times that, and we can reach contradiction for these things. And for this case we can say k minus 1, k plus 1 minus b equals 0, or k plus 1 minus b equals 2k minus 1. Let's at first consider only these three cases. From this one we could conclude that b equals, if you take this to this side, 3k, and we can cancel plus 1 from both sides. B equals 3k, and 3k must be less than 2k plus 1, and then k is less than or equal 1. We can here say, okay, it is only for 3 elements, or we can say at first we said k is greater than equal to, so it's contradiction. And if you consider, for example, minus 2 times this, then b would be greater. Again, another contradiction like this. Let's consider this case. In this case, we can conclude b equals k plus 1, but from here a equals b, and we reach contradiction, okay? And in this case, k plus 1 minus b equals 2k minus 1. So from this case, we can conclude b equals k plus 1 minus this would be minus k plus 2. And we know that it must be greater than equal 1, so k is less than, we conclude that k is less than equal 1. And again, another contradiction, because at first we assume that k is greater than equal to. So for k greater than equal to, the problem is not true. So the only n that satisfies the problem is when n equals 3 or 1, but the problem says n is greater than equal to, so the only answer is this, since n is greater than equal to from the assumption of the problem.